Hello everyone, my name is Tomáš and I'll talk about our work on finding the hardest formulas for resolution. The motivation for this work can be summarized by the following question. How hard can it be to prove a formula compared to its size? So our setup is propositional logic. We're working with CNF formulas, which I'm sure most of you are familiar with. And as the title suggests, we're working with a proof system called resolution. So every unsatisfiable formula has a resolution proof. If you're not familiar with resolution, it consists of one single resolution rule, which tells you that if two clauses clash on a variable, you can remove the variable and take the union of the rest of the clauses. And the resolution proof of a formula is simply a sequence of clauses that can be derived by a resolution, such that the last clause is the empty clause. And the resolution hardness of a formula is simply the length of a shortest proof that a formula has. The resolution hardness is interesting because it gives a lower bound on the running time of modern set solvers based on conflict-driven clause learning, and as such it has been studied a lot in proof complexity, and many families of hard formulas such as the pigeonhole principle are known, so families that require super polynomial proofs in a resolution. So, but here we take a slightly different approach and we look at the resolution hardness exactly. We ask this question: how hard can a formula with m clauses get? So we define the resolution hardness numbers. So the mth resolution hardness number hm is just the length of the largest proof length the formula with m clauses requires. So this is really some sort of exact version of proof complexity. And our goal is to understand how these hardest formulas look, how fast the resolution hardness numbers grow, and possibly discover patterns that can be generalized to infinite families of formulas. Okay, one remark: we could also define the hardness numbers in terms of the number of variables, but that would not be very interesting, and you can check that in that case the hardness number would simply be 2 to the n plus 1 minus 1. Alright, so our contributions in this paper are threefold. First, we do some candidate filtering to theoretically to narrow down the search space for hardest formulas. So we determine a small set that must contain some hardest formula with m clauses. Then we do symmetry breaking search using the graph isomorphism package naughty to compute the sets chi-m that contain the hardest formulas up to the value of m equals 10. Finally, we compute shortest proofs of all the generated formulas using a novel set encoding that we propose for this problem. And so below you can see the values of the hardness numbers. The reason why we stop at m equals 10 is that both the formula enumeration phase as well as the computation of the shortest proofs of the hardest formulas become a bottleneck at this point. So there's an interesting aspect of this work in that we use a resolution-based subsolver in order to analyze resolution itself. So in a way, it's a bit like these two hands in the famous picture of M.C. Escher, which paradoxically draw each other into existence. And so with that, I'd like to conclude the introductory part and move on to the technical part of the talk. And so I'll begin with computing the resolution hardness numbers. So our strategy is, first we define the set h of m, which is just the set of the hardest formulas with m clauses that have the highest resolution hardness. And of course, what we need to do is we need to try to find a formula in h of m and then compute its shortest proofs. And that is hm, the hardness number. Okay? But it's unclear how to obtain an element from hm directly, efficiently. So what we do is we will enumerate a set of formulas chi of m that has the following properties. It intersects with h of m, so that it contains a hardest formula. It should be as small as possible because we're going to enumerate it. It should be enumerable reasonably efficiently, let's say. Okay? So, and then what we simply do is we compute the shortest proofs of all formulas that we generated, and the highest one is the hardness number. Alright, so that's the overall strategy, high level. And of course, an obvious candidate for chi of m would be all unsatisfiable formulas, or even all formulas, but that is simply too large, so we want to narrow that down. Okay, and it turns out that an important concept that we'll use is that of saturated minimally unsatisfiable formulas. So first, a formula is minimally unsatisfiable if removing any clause makes it, if it's unsatisfiable and removing any clause makes it satisfiable. And it's saturated minimally unsatisfiable if additionally adding any literal to any clause also makes it satisfiable. All right? And there's this fundamental theorem about minimally unsatisfiable formulas that bounds the number of variables if we know the number of clauses. So for arbitrary formulas, in theory, if you fix the number of clauses, the number of variables could still be arbitrary, but not for minimally unsatisfiable formulas. Okay, so we're trying to narrow down the set chi of M that we're going to enumerate. So first theorem that we show, all formulas in all of the hardest formulas are minimally unsatisfiable. Okay, so we can restrict ourselves to minimally unsatisfiable formulas. And also, there is a saturated minimally unsatisfiable formula that is among the hardest ones. Okay, so we will only generate the SMU formulas, saturated minimally unsatisfiable, and compute their shortest proofs. So, yeah, just a bit of notation. So SMU of M will simply be the set of SMU formulas with M clauses. And so it looks like something like this. There's a set of unsatisfiable formulas with M clauses, then minimally unsatisfiable that's contained inside, and then saturated minimally unsatisfiable, and has an intersection with the hardest formulas, right? So that's what we're after. Okay, so how do we generate these saturated minimally unsatisfiable formulas now? So we only want to generate non-isomorphic formulas because isomorphic formulas have the same properties and also the same hardness. What we do is we use the graph isomorphism package naughty. And so in order to be able to use it, we have to represent formulas in some way as graphs, because that's what naughty works with. So to that end, we define the clause literal graph of a formula as the undirected 2 graph. 2 graph just means that the vertex set is split into 2 partitions. So one partition is the literals of f, and the other partition is the clauses of f. And we have edges between a literal and a clause if the literal is contained in the clause. And we also have an edge between the 2 literals of every variable. Okay, so here's a simple example. We have a short formula, and this is the clause literal graph. Okay, and then it's not too easy to see, not too hard to see that that the clause literal graphs are a good representation of formulas with respect to isomorphism. So 2 formulas are isomorphic if and only if their clause literal graphs are isomorphic, where the isomorphism of the clause literal graphs has to respect the partitions, right? So that's exactly the definition of formula isomorphisms. So what we will do is we will generate these clause literal graphs with naughty, but that's going to be the expensive part, so we want to improve that further. So and another notion that we're going to use there is that of singular variables. So a variable is singular in a formula if one of its literals only occurs once. Okay, and then another notion is that of DP reduction. And so if you take a variable of a formula, then the DP reduct is obtained simply by performing all resolutions on that variable and then removing all clauses that contain the variable. Okay, and there's this fundamental lemma that connects a saturated minimal unsatisfiability and singular DP reduction on singular variables. And so it says that if x is singular in a formula f, then f is saturated minimally unsatisfiable if and only if the DP reduct is also saturated minimally unsatisfiable, and it will have one fewer clauses. And this lemma also says some more things that are also useful, but this is the sort of the main thing. Okay, so how do we use this? So we define, we say that the formula is singular if it contains a singular variable, and we say it's regular otherwise. Okay, so thanks to this lemma that I just showed, if we have all saturated minimally unsatisfiable formulas on M clauses, we can use DP lifting, what we call DP lifting, which is just reverse DP reduction, to generate all of the singular formulas, singular saturated minimally unsatisfiable formulas, with one more clauses. Okay, so what we can do now is we can restrict ourselves to generating regular formulas, and then the singular ones we compute in a post-processing step using DP lifting. Okay, so that's for the regular formulas. And one other thing we can also do is we can directly show some hardness results for formulas of deficiency 1 and 2. So the deficiency of a formula is defined as the difference between the number of its clauses and the number of its variables. And by the lemma about minimally unsatisfiable formulas that I showed earlier, we know that the deficiency of a minimally unsatisfiable formula must be positive. Okay, and it's also known that if you want a regular formula of deficiency 2, a regular minimally unsatisfiable formula, then it's unique. There's only one such formula up to isomorphism. And it's also saturated. Okay, and we can use this and other known results from the literature to prove the following theorem. So if F is minimally unsatisfiable, then if it has deficiency 1, its hardness is 2m minus 1, so it has a read once proof. And if its deficiency is 2 and it's regular, so it's this unique deficiency 2 regular formula, then its hardness we show is 3m minus 5. Okay, so we don't have to actually compute any shortest proofs of these formulas because we know what they look like. All right, and that's all for the formula enumeration phase. So now we can put it all together. So what we do is we use a special adaptation of Naughty's GenBG utility that generates bipartite 2 graphs. So the modification is that now it generates closed literal graphs in order to enumerate a set high M, which contains all the RSMU formulas, and then we test each generated graph for saturated minimal unsatisfiable. So we cannot generate SMU formulas directly, but we do it sort of indirectly. But then we obtain the sets SMU, and we only compute their shortest proofs. There are some technical optimizations, such as we have Naughty gives you access to the intermediate graphs that it builds, so we can already test some properties there, and we also found out that it's much better if you have to call a stat solver many times with very easy formulas. Might be better to use brute force actually rather than stat solver. There are some convenient data structures in Naughty for that, so that brought a huge improvement for us. Okay, so now we generated all the RSMU formulas, and then we use DP lifting to compute all the SSMU formulas. We have all the SMU formulas, and then we simply compute all the shortest proofs, and we get the resolution hardness numbers. Okay, so now the last missing piece is how do we compute the shortest proofs. So I'll get to that now. So the problem computing shortest proofs. So the optimization problem is given a formula, compute its hardness, so the length of some shortest resolution proof. We can turn it into a decision version. So for a given integer s, does f have a resolution proof of length at most s? So the first thing we can do is we can look at the computational complexity of this problem. So it's not too hard to see that it's co-MP hard, and it also is in non-deterministic exponential time, and it's actually an open question what the precise complexity of this problem is. And so I should say that S is given in binary here. So our approach is we encode the decision problem into SAT, and then we call the SAT solver with different values of S and until we find the shortest proof, so the traditional way. Okay, so I'll just briefly repeat that resolution proofs for us are simply sequences of clauses such that each clause is either an axiom of the input formula or is a resolvent of 2 previous clauses of the sequence. Now the core of the encoding is captured in the variables that describe the clauses of the sequence, and also variables that describe that basically describe the resolution steps. What are the premises of resolution steps? I don't want to go too much into the basic details of the encoding because a similar encoding has been proposed before, but we have some crucial differences that are focused on minimally unsatisfiable formulas. So one thing is, for instance, we know we have to use all axioms. We know that every clause must be used, so we get some bounds on the proof size. We can also introduce some additional constraints that track how often clauses are reduced, how many times, and then as the solver tries to find the shortest proofs, it can detect dead branches earlier. The one thing that I want to talk about a little more is symmetry breaking. So if you have a proof that's a sequence of clauses, we can associate a directed acyclic graph where the arcs are just given by the resolution steps. So if 2 sequences have the same DAG, then they're really just 2 different topological sorts of the same proof, right? So you want to make sure that we only accept one topological sort of each DAG. So we define the canonical topological sort of some DAG G in the following way. So first we define an arbitrary total order on the vertices of G. So the vertices of G in our case will be the clauses of the proof. And then the canonical topological sort is obtained by the topological sorting procedure, which always picks the largest eligible vertex under this total order as the next vertex, okay? And so this total order we define on clauses as the lexicographic order with some fixed order on literals. Fix an order of literals, take the lexicographic order on clauses, okay? And then we add constraints to make sure that we only, the only kind of proofs that are accepted are canonical topological sorts, okay? So that's the symmetry breaking. And that's really it about the encoding, and so we can move on to the results section. So first of all, and most importantly, the resolution hardness sequence. So here it is. Now maybe it becomes a little clearer why I underbraced the two segments with these linear relationships. So the first one comes from deficiency 1 formulas, and the second one comes from the unique regular deficiency 2 formula, which is always among the hardest formulas. In some cases there are also other formulas that have the same hardness, but this one is always among the hardest formulas, and hence it's 3m minus 5. And then at m equals 10, finally the deficiency 2 formula is no longer among the hardest ones, and there are actually other hardest formulas, right? So this table gives a slightly more detailed picture. Here are the hardness numbers broken down by the number of variables as well, right? So on the rows are the number of variables and the columns are the number of clauses. And so in each cell we have the length of the longest shortest proof required by a formula with n variables and m clauses, okay? And in the parentheses we have the number of regular formulas that attain maximum hardness in that cell. We have found that in almost all cases that the hardest formulas are always regular, with the exception of 7 variables and 10 clauses, where there are also 19 singular variables up to isomorphism among the hardest ones. Okay, so this is the detailed picture of resolution hardness broken down by the number of variables. Here we have the clause literal graphs of the 3 hardest formulas with 10 clauses. If you look back at this table, 6 variables and 10 clauses, we have 3 hardest formulas. Deficiency 4, so here they are. So the squares are the clauses and circles are the literals, and this is the clause literal graph. Okay. Here we have the numbers of RSME formulas broken down by the number of variables and clauses, so how many there are modulo isomorphism, and here we have the singular formulas. So we can see that by restricting ourselves in the generation phase to just regular formulas, we saved quite a bit of effort. Okay, so the regular formulas, the singular formulas. So and finally we get to the end. So to summarize, we developed a set encoding for the computation of the shortest proof of a formula with novel symmetry breaking and one that is targeted towards minimally unsatisfiable formulas. We found out that RSME formulas are particularly important when it comes to resolution hardness. And then we generated all these RSME formulas with DP lifting also SSME formulas, and we computed all the shortest proofs, ultimately determining the first 10 values of the resolution hardness sequence. So some observations and open problems. Our results highlight the importance of RSME, so the natural question, is it true that the hardest formulas are always regular? One interesting aspect is that we have not seen hard formulas from proof complexity. So for instance, the pigeonhole principle with 3 pigeons and 2 clauses, 3 pigeons and 2 holes has 9 clauses and 6 variables. So it is in scope of our methods, but it's actually neither saturated nor regular. And it so happens that as soon as a formula is not saturated, this singularity lemma doesn't apply, and singularity is no longer a source of easiness. So that's one interesting phenomenon. And finally, this open question of the computational complexity of computing the shortest resolution proof, where I should repeat again, S is given in binary, the length of the proof. Okay? And with that, I conclude the talk. Thank you for your attention.